Hi, in this lecture we're going to do chapter 24. This chapter is very important for engineers and also anyone who is interested in science because in this chapter we're going to learn alternating current and we're going to talk about also waves because the alternating currents are actually waves. So let's start with the basic definitions. Okay, so DC current is basically, it means DC means a direct current, and now you're going to understand why it's called direct current. So the voltage in DC current is time independent, so it doesn't depend on time. So if you have something like this, a 9 volts battery, okay, and if you connect it to a circuit, the voltage that it provides is always the same. It's 9 volts, and it doesn't change. Okay, it doesn't change with the time. And if you remember from the earlier lectures, the DC source, for example battery, is shown with this symbol. Okay, now look at this animation. So if you connect the battery to a circuit, so basically the charge will flow, the current will flow from positive terminal to the negative terminal, and you can see that the flow of the charges is they have the same speed. So that also means the current is the same, the voltage is the same. So this is a circuit of direct current. Now let's come to the AC current. So AC means alternating current. Alternate means change. Okay. So the voltage and also the current that we're going to see in the following slides, the voltage is changing with time. Okay, so where can you find AC current? One example is the outlet, right? The sockets on the walls, so they provide AC current. Okay, so if you try to measure it with let's say with an oscilloscope, so what you're going to see is the current or the voltage is it starts from 0, it becomes, let's say, 10, 20, 100, 222, and then it starts decreasing like 200, 150, 100, 0, and then it becomes negative, and then it becomes positive again. So it oscillates between positive and negative. Of course, it has a maximum and a minimum. Okay, now we're going to see in the next slides that the AC source is shown with this figure. Okay, this you can see that this is a wave sign. Okay, so basically if you look at this diagram, this animation, so this is an AC source. Okay, for example, it's coming from this wall socket. You can see that the current goes to the left, right, or clockwise and anti-clockwise all the time, right? So it's not like direct current, which is in the same direction all the time. The AC current oscillates back and forth. And you can also see that the speed also changes, right? At some points the speed is 0, that means the current is 0 at these points. And then sometimes it becomes maximum and minimum. Okay, so these are the basic definitions. Now, what are the uses of AC currents? Well, AC circuits are the basis of almost all technological devices. So for example, if you think about a radio, okay, so the radio signals are AC signals. Okay, they're alternating electromagnetic waves, and to catch them, you need a RLC circuits that we're going to learn in this lecture. Also walk through metal detectors that we see almost everywhere. They also work on the principles of AC currents. The other thing is we learned in the previous lecture, the transformers, they basically increase or decrease the voltage or the current. For example, if your cell phone is working with, let's say, 4 volts, and if you want to charge it, you cannot directly connect it to the wall socket because it's 220 volts. So you have to use adapter that would decrease the voltage from 220 to 4 volts. Okay, inside it there's a small transformer just like this one. But these transformers, they work with AC currents, not DC currents. Okay, so again, AC currents are useful because you can actually change the voltage and the current by using transformers. Okay, so let's continue. Now the question is, how do you produce AC currents, right? So we actually learned about it, right? If you think about the generators, that's what electric generators do, right? So they generate electricity basically by converting mechanical energy or mechanical input to electrical energy. So if you basically turn this shaft, you can turn it with your hand, you can turn it with wind power, you can turn it with, in a dam with water flowing down, in any way. So this thing, this loop inside this magnetic field will turn, right? When it turns, because the magnetic flux is changing here, it will create, so remember the flux definition, it's B times A times cosine theta, okay? So now B is the magnetic field, A is the area here, and angle is the angle between the surface, let's think about this vector, between this vector and the magnetic field. So that angle, if you take the cosine of that angle and multiply with B and A, you're going to find the flux. And because this is, if this is rotating with angular speed, then you can write theta, the angle, because the angle will be changing now. You can write it as angular speed times time, right? So this is the flux. It depends on time because the angle is changing here. Now, if you remember from the previous lecture, so a voltage is produced here in this circuit, right? And it's basically N, which is the number of loops here, which is 1 in this figure, times the change of flux. I wrote it here as derivatives, but you can write it also as in terms of delta. You can write it in terms of delta, which would mean change, which is pretty much the same thing. And well, basically the derivative of this with respect to time will give you a sign. Well, it actually gives you negative sign, but I'm considering the absolute value here. So it's going to give you sine, and if you use the chain rule, it's going to give you also omega. So this is the voltage that's created here. Now, if you look at here, now this part is some constant number, right? And that part is actually here, the maximum and minimum values. Now, sine is some function which oscillates between -1 and +1. So basically, this voltage will oscillate as time goes on. It's going to oscillate between this number and that number. So this is how you can generate electric current, AC current, and you can connect it to a light bulb, okay? So of course the current all the time, it passes to the right, to the left, to the right, so it's alternating current, but for the light bulb, you will not really notice that back and forth change because it's usually like 50 hertz, like 50 times in a second or 60 times in a second. But if you have really low frequency AC current, then you can actually see the flicker on the light bulb. Okay, so this is how you create an AC current. Now, so I mentioned these before, these concepts, the frequency, angular speed, or angular frequency, and the period, but this is really important, so I'm repeating here. You have to understand these concepts really well, like you have to digest them, okay? So frequency, basically it means how many oscillations in 1 second, or how many times something happens in 1 second, okay? Now the unit is 1/2 seconds, or you can also use hertz, okay? So for example, if 3 oscillations happens in 1 second, that means the frequency is 3 hertz. Now look at this plot. So one full oscillation is, so it starts from 0, it increases, and it comes back here. So this is one oscillation, one full oscillation. So you can see here, goes up and down, comes back to 0. This is one oscillation. This is the second one here. And this is the third one. Now look at, in 1 second, how many oscillations? There are 3 oscillations. So that means the frequency here is 3 Hertz. Now, what about the angular speed or angular frequency? Same thing. So in this context, it's going to be angular frequency. It's basically you multiply the frequency by 2 pi. Now, in the following slides, you're going to see that the oscillations, like these sine waves, are actually related to rotation. You will see that. That's why this is called angular frequency, and we're actually multiplying it with 360 degrees, right? 2 pi is 360 degrees. So, well, this basically also means how many radians, which is angle, right? How many radians does it turn in 1 second? Now, look at this shaft. So this shaft turns, and it turns this circuit. The question is, if you want to know what omega is, which is angular frequency, you have to answer the question, how many radians does it turn in 1 second? So one full rotation is 2 pi radians, right? 360 degrees, 2 pi radians. Okay, let's before going to the examples, by the way, this is in SI units, it's radians per second. Now the conversion is like 1 revolution per second. So when you do 1 revolution, it means 360 degrees per second. Or if you want to write this in terms of radians, it means 2 pi radians per second. And you know 2 pi is approximately 6.28. Okay, this is 6.28 radians per second. Okay, let me give you an example. So 180 degrees in 1 second. Let's say this shaft or this circuit rotates 180 degrees in 1 second. Okay, now what is the angular frequency? Well, in 1 second, if it rotates 180, that means pi over 2. Remember, it's in units of radians, so I have to convert it to radians. So this is basically pi over 2, right? So it's pi over 2 radians per second. This is the angular speed. Okay, another example, if the frequency is 3 Hertz, which is here, plotted here, then the angular frequency becomes 2 pi times 3, which is 6 pi radians per second. What does that mean? Well, it means the generator shaft, this shaft here, it rotates 6 pi radians in 1 second when the frequency is 3 Hertz. Okay, so you have to use radians per second for formulas that include omega. Okay, for example, remember this formula from the previous slide. So here you cannot use revolutions per second, you cannot use degrees per second, you have to use radians per second in the formula. Now, lastly, the concept of period it's basically 1 over frequency, and it answers the question how long in seconds one full rotation would take. Like how many seconds does it take for one full rotation? It could take 5 seconds, it could take 0.1 seconds. So for example, if the frequency is 3 Hertz, then the period will be 1 over frequency, which is 1 over 3, which is approximately 0.33 seconds. Okay, now look at the graph. Okay, one full oscillation, so it takes about this much time. Now look at this time. This is the time that it takes for one full rotation, which is the rotation of this shaft or this loop for 360 degrees. It takes this much time, 0.33 seconds, and this is the period. Okay, so let's continue. Now, let's talk about AC currents. Now we're going to add, so first we have this AC source. Now we're going to add resistors, we're going to add capacitors, inductors to this circuit, but first we're going to start with the easy one, which is the resistor, okay? Now let's first talk about like what is the specs of this AC voltage. Well, if you're in the US, then it's 120 volts and it's 60 hertz. When you are in the European countries or Turkey, then it's 220 volts and it's 50 hertz. So if you buy something in the US, some device or some appliance, if you bring it to the European countries or Turkey, then it's not going to work. It's not enough to change the voltage, but also the frequencies are different, right? So also remember that the angular frequency again is 2 pi times the frequency. Okay, so basically if you look at this circuit, so this frequency is also related how many times the current makes back and forth in 1 second. So this is here, it's really slow, right? The frequency is probably I don't know, 1 or half, but at our houses it's about like 50 hertz. So this this back and forth happens 50 times in 1 second. Okay, so let's say we have an AC source and it's connected to a resistor. The resistor could be a light bulb, okay, it could be a heater or something like that. Okay, now so if you ask what is the current here, how do you calculate it? It's going to be the voltage on the resistor divided by the resistance, right? Now the voltage is, so it's a sine wave, right? It's a sine wave. So I can write it as the maximum voltage. So let's look at here, the voltage at any time. So this is time at any time. This is a function of time. Okay, so the voltage at any time will be the maximum value, which is this number. So let's say if you're in Turkey, it's going to be 220 volts. So yes, 220 volts. Okay, so this maximum is 220. And there's going to be the sine omega t term. So instead of V, we can write V max times sine omega t. This is VR. Okay, and this part gives you the maximum current, and we also have sine omega t. So this is going to be the current in the circuit. Okay, so we have this current in the circuit, and we have this voltage on the resistor. Now, voltage and the current on the resistor are in phase when there's only resistors in the circuits and no capacitors or inductors. So here in phase means the voltage and current increase and decrease at the same time. Now look at the current. So the current increases and the voltage increases at the same time. The current decreases and the voltage decreases at the same time. Okay. Now in the following slides, we're going to see when we add capacitors or inductors, these are not going to be in phase. For example, as the current increases, maybe the voltage will be decreases. It will decrease like this, for example. We will see. But here at this point, if you have only a resistor in the circuit, then the voltage and the current, they are in phase. You can see that they become maximum at the same time, they become zero at the same time, and they become minimum at the same time. So this is called in phase. If you have two waves, here the voltage and the current, if they do exactly the same thing at the same time, then that means they are in phase. Okay. By the way, they don't have to have the same amplitude. They can have different amplitudes. For example, Imax is small. If you look at the plot, Imax is smaller than Vmax. Okay, that's fine. But if they do the same motion at the same time, then we call them in phase. Okay, let's continue. Now, this is a general. Now, in this slide, I'm going to talk about what it means, the phase of the wave. So you have to learn this because you're going to need this concept anywhere, like everywhere in your professional life as an engineer or scientist. Okay, so this is basically, so phase of a wave, what does it mean? Basically tells us for how many angles the wave is shifted. Okay, so let's say you have a sine wave that's shown in this blue plot. Okay, now if you add negative pi over 2, which is 90 degrees, now look what happens. You still have the same sine wave. Look at the heights. The amplitudes are the same. The frequencies are the same. See, if this makes one full motion in 2 pi, so in time 2 pi makes one full motion. Now look at the yellow one. So it starts from here, one full motion here, and this is also 2 pi, right? So the frequencies are the same, amplitudes are the same. Okay, the only difference is the yellow one, the dashed yellow one, is shifted to the right. And that shift is coming from here. This is the phase, and it's usually shown with Greek letter phi. Okay, so you can play with the phase phi, and you can shift the waves forward or backward, or to the left or to the right. Okay, so there is pi over 2 radians or 90 degrees difference. There is 90 degrees difference in phase between the two curves. Okay, so the two waves are not in phase. When the difference is 0, then they become obviously in phase, but here they are out of phase. So the yellow dash curve lags behind, comes after in time, lags behind the blue curve by 90 degrees. Now what does it mean? Now look at the curves. Now you may be confused here because the yellow curve is actually in the forward, like it's to the right. So you may see that it's actually maybe the yellow. You may think that the blue is lagging behind the yellow, but now look at this. Who is becoming maximum? Which one becomes maximum, reaches the peak in time? So the blue curve, it reaches the peak at time pi over 2, but the yellow curve reaches the peak at pi. So the yellow curve reaches the peak at a later time. So this one is late. The yellow one is actually late. The blue one is early. So this is why we say the yellow dash curve, it lags behind. It comes after in time the blue curve. Now what is the lag? It's pi over 2. You can see it here or you can see it here. The lag between the yellow and the blue curves is pi over 2. Okay, let's see the next one. Now, instead of looking at the sine wave plot, we can also use the phase vectors. So now I'm going to introduce what phase vectors are. So these are the phase vectors. So the blue vector is for the blue curve, sine t, and the yellow vector is for the yellow curve, which is sine t minus pi over 2. So this phase vector is called phasor. It's a made-up word from the two words phase plus vector, so it's called phasor. So these are called phasor, and these also phasor diagrams. Okay, so the instantaneous value, instantaneous means at that moment, of the voltage or current at any time is given by the y component of their phasor. So let's see, at time 0, now let's look at the phasor, blue phasor, which is for this blue curve. Okay, what is the y component of this blue phasor? Well, the y component is 0. That means the value of this blue curve is 0, which is right. Okay. What about the yellow one? So the phasor is down. What is the y component? Well, imagine these have length 1. Okay. So the y component is 1, but it's actually -1. So the yellow curve is at -1. Now let's look at this one. Now the blue is at, actually the y component is 1, which is, you can see that the blue curve at time pi over 2, its y component is 1. You can see it here, same thing. And the yellow curve's y component is 0, and you can see that it's actually 0. So it goes like this, okay? And at this point, you can see that the yellow curve has a positive y component. Here it has a positive value. At this point, you can see that it's a positive value. And the yellow curve, it has a negative value, and you can see that it has a negative value. Okay, so here it says, instead of looking at the sine wave plot, we can also use the phase vector. So all the information here in the sine wave plot, it's actually encoded here into the vectors. Okay, now it's easier to look at the vectors than the sine waves. That's why we're going to use phasor diagrams. Okay, so it's another way to show the waves, basically. Now the other thing that I want you guys to see, that the vectors are actually rotating counterclockwise, right? As time goes on, they are rotating, and this rotation angular frequency or angular velocity, angular speed of this rotation is actually omega. It's going to be the frequency. Here you can see that there's actually omega here. In this example, omega is 1. 1, let me try to write it, 1 radians per second. Now look at this one. When it rotates 45 degrees, it becomes like this. When this rotates 45 degrees, it becomes like this, and so on and so forth. Okay, so here basically we introduce the phasors. Again, these are just another tool. This is just another tool, phasor diagrams, to analyze the waves and their phases. Now, one last thing here. Now, look at the angle between these two vectors, the yellow and the blue. These are rotating in counterclockwise. So that means the yellow is 90 degrees behind the blue vector, right? Blue phasor. So that also means the yellow curve is 90 degrees behind the blue curve. Now look at the peak points. The blue curve happens, it peaks first in time, and then after time, after the period of pi over 2, which is 90 degrees, the yellow curve peaks. So the yellow curve is late. It's coming behind the blue curve for how much degrees? 90 degrees. And you can see that the yellow curve is actually behind the blue curve. Again, imagine that these are rotating counterclockwise. So the yellow phasor is behind the blue phasor by 90 degrees. Look at here, it's again 90 degrees. It's always 90 degrees. This angle doesn't change. Okay, so there is a couple of new concepts here, like the phase and the phasors. So you may want to listen to these slides again, maybe pause and get back and then listen again. So it's important that you understand these concepts like the phase and the phasors, okay? Because we're going to use them in the next slides. Okay, let's continue. Now I'm going to show you how we use phasor diagrams for the first circuit that we did, it's basically an AC circuit with resistor R. Okay, again, this resistor could be a light bulb, it could be a heater, anything. Okay, so now how do we use the phasors with a circuit with an AC circuit with only R resistance? Okay, now below, so let's start from here. Below Vmax is the maximum voltage. Okay, so it's basically here. If you connect it to the wall in European countries, it's going to be 220 volts maximum voltage. Sorry, it's not 220 volts, it's actually more than that. I'm going to explain it later. So the voltage on the resistor are, so Vmax is the voltage on the resistor, or V at any time. And Imax is the maximum current passing through the whole circuit. So it's not only necessarily the current passing through this resistor, it's actually passing through the whole circuit. But when we talk about V, we're talking about the voltage on the resistor, okay? So the projection of the phasors, projection means the projection of the phasors on the y-axis. It basically means the components of the vectors, the y components, here this distance or the whole thing, is the current and the voltage at that time, okay? So the current and the voltage, they have different values at different times, right? So these are I of t and v of t, and there is also the maximum values like the maximum current and the maximum voltage. Okay, so for an R circuit with AC source, that means you only have R resistance, not a capacitor, not a inductor in the circuit. There's 0 degrees between the phasors, which means phase vectors, between the maximum value of the voltage on the resistor and the maximum value of the current passing through the circuit. That means V and I on the resistor are in phase. I actually talked about this in the previous slide, right? Here again, I repeat the same plot here. So as the current, is 0, voltage is 0 at 0 times 0. They peak at the same time. They become again 0 at the same time. They become minimum at the same time. So they are in phase. Okay, so that means if I draw the phasors, now this green phasor is for the current, and this brown phasor is for the voltage. Okay, and this is for the current. Now, because these are in phase, that means there is 0 degrees phase difference between them. Let me go back. When there's phase difference, see, they look like this. They don't become maximum or minimum at the same time. They peak at different times, right? There's a phase, but when you make this number 0, they will be the same waves on top of each other. So there will be 0 phase, right? So if you have, let me go back. If you have just a resistor, there's 0 degrees between the current and the voltage. So here the current phasor, the voltage phasor, and the angle between them is 0. And this vector is actually rotating counterclockwise all the time. So as time passes on, it's going to be like this. Okay, and at some point it's going to be like this. When it's exactly on the y-axis, it actually corresponds to this maximum values, right? And it's going to continue rotating, so it's going to be, so those two vectors will be like this, for example. Here, the y component is 0, right? This actually corresponds to this point. And then when they point down, it corresponds to this minimum of both sine waves, right? The voltage and the current. But the point here is there is 0 degrees between the current and the voltage on the resistor. You will see that there's going to be some angle between these when we add a capacitor or an inductor to the circuit. Okay, so the bottom line here is if you have only resistor in the circuit, the phasors, they have 0 degrees between them, and the current and the voltage, they are in phase. In phase. Okay, let's see the next one. Now, in the US, the AC voltage is 120 volts. That's something I said before. And in Europe and Turkey, it's 220 volts. Now, these are actually root mean square values, not maximum voltages. Okay, now I'm going to explain to you what root mean square is, but you can think of it roughly as average. Now, think about the voltage. So the voltage is actually like this, right? It goes like this. It becomes negative and positive. But if I add, if I connect it to a light bulb, it doesn't matter if the current is past, it's negative or positive, like it's flowing to the left or right, because it doesn't matter if you have a resistor like a light bulb, then whether it's, the current is to the left or right, it will still produce the same light. It will consume the same power regardless of the direction of the current. So instead of looking at the voltage with positive and negative, then I should look at the absolute value of the voltage, okay? So this is what's actually, what's relevant. Now, if you look at the voltage, it starts from 0, it becomes maximum, and then becomes 0 and maximum. So I'm not going to get the maximum value of the voltage from the AC source all the time. It's only one moment, right? It's only one moment. So on average, the voltage is not 0. The voltage is not maximum, but on average, it's going to be somewhere in between, not exactly the middle point. Like you have to use some integral and averaging to calculate it, time averaging. This is time. You can do it actually. You can take the integral of these curves. It's basically sine squared, and take the time average. So basically divide the period of time. You can find this is not exactly the RMS value, or the average is not exactly in the middle, but it's something like this. The relation is something like this. So basically, if you divide the maximum value by square root 2, which is like 1.4, you would find the RMS voltage. Again, think about it as an average. So in Turkey or Europe, the RMS voltage is 220 volts. Okay, so but if you ask what is the maximum voltage, it becomes maximum. So basically multiply this by 220 times. So multiply 220 by square root 2. So the maximum is 310 volts. So the maximum is 310 volts. But again, you get, yes, do you get 310 volts from the outlet? Yes, but it's only at some moments. You don't get 310 all the time. That's why we have to think about the average voltage. Okay, so for Ohm's law and the average power, you have to use not the maximum value of the voltage. Again, practically it's not the value that you get from the outlet. So you have to use the averages, which is the RMS values of the current and the voltage. So if you want to use the Ohm's law with the RMS voltages, it's here. And if you want to calculate the power, so you can use I squared R, or you can use V squared divided by R. But again, you have to use the RMS values. So the bottom line is, practically, if you want to run some appliance or some device, it's the maximum values are not really important. So what you get is basically you can think of you're running the devices with the RMS values. Of course, the maximum could be relevant if if the voltage can handle only up to some maximum values, then you have to be careful about the maximum, but practically it's the RMS values. Okay, so now we are moving into the subject of capacitors in AC currents. Now throw away the resistance. Now we're going to only use the capacitors with the AC circuits. But before that, let's remember something from the earlier chapters. With DC currents, let's say we have a battery like this, the capacitor would get charged. So now this is the positive terminal, so the current will flow clockwise here, and this side will be positively charged, this side will be negatively charged. And when this is completely charged, the current will stop flowing, because now if this is, let's say, 9 volts, the battery is 9 volts, this is going to be also 9 volts. And you can see that they would be two 9 volts battery connected in opposite sides, so plus is connected to plus. So the current would stop flowing when this is completely charged, okay? As the field capacitor will act as a broken line. When there's no current, you can think of this capacitor is now acting as a broken line or broken wire. So you can show it, but this is when the capacitor is completely charged. When the capacitor is completely charged, this circuit becomes like this. And you know that when the line is broken, then there is no current in the circuit. Okay, what happens with the AC current? Let's think about it. Now, with the AC current, let's say initially this part is 0. Okay, now that means the capacitor will start charging, well, having plus side here and negative side here. But this AC source, the current will flip shortly, and it's actually like really fast, like it flips direction 50 or 60 times in 1 second. So now instead of plus, now this side will be negative. So if this side is negative, this is already charged a little bit. So what's going to happen is this is going to start discharging. So this side, so it's going to start discharging. Now again, this is going to flip. It's going to become plus, and the capacitor will start again charging. So the capacitors with the AC current is constantly charging and discharging because the direction of the current is constantly changing. So that means there's going to be always a current on the capacitor back and forth, right? It's not like the DC current because the capacitor is not getting fully charged, right? Because the current is, even if it charges a little bit, then the current flips and it starts discharging. So it never becomes a broken line in AC currents. Now you here learn that the circuit elements like capacitors, inductors, they act differently in DC current and AC current. So this is important. Now let's look at the next one. So in the previous slides, we had a resistor here, right, with AC source. Now we have a capacitor, okay? So we have a AC source here. So VRMS is the RMS voltage, so it could be like 220 volts, okay? And this is the frequency, sorry, the angular frequency. It's actually 2 pi times F. So in Europe, it will be 60, I think. Let me go back. So in Europe, sorry, it's 50 hertz. So it's going to be, let's say, 50 hertz. It could be something else. And we're connecting to this voltage source, a capacitor. What happens? Okay, so let's say if VRMS could be 220 volts, and omega could be 2 pi times 50 hertz, okay? Of the AC sources given, let's say these are given, how can I calculate IRMS? So what is the RMS current passing through the capacitor or the whole circuit? Okay, what is the RMS current passing through the circuit? Okay, now we have, so we have a relation. It's similar to Ohm's law. So V is the same except we are going to use VRMS. I is the same except we are going to use IRMS. Now instead of resistance, where we have in resistors, now in AC circuits, the capacitors, they have something called capacitive reactance. So this chi sub C, or we can call it XC, this is capacitive resistance. It acts like R in the Ohm's law. So you remember that R is in units of ohms, and the capacitive reactance is also in units of ohms. Again, just look at the analogy. This is just like the Ohm's law. Instead of resistance, we have the capacitance. Sorry, the capacitive reactance. Okay? So now, so what is the formula for that capacitive reactance? So it's actually 1 over omega, which is the angular frequency, which is 2 pi f, f is frequency, times the capacitance of the capacitor here. Okay, so then this capacitive reactance, it actually, so the capacitor reacts to the voltage. So it's just like the resistance is reacting to the voltage. It basically uses, some of the energy. So the capacitor is also reacting the change of current or the change of voltage in the AC circuit. So that's why it's so this word reactance, it's coming from reaction, and the capacitive reactance XC, it basically determines the current in the circuit. Okay, I'm going to talk about impedance later. Let's cross this out. Okay, so IRMS, the RMS current in the circuit, it depends on the capacitance and the AC source's frequency, right? So if you want to calculate here, it depends on the AC source's frequency. So it's going to be different in the US. It's going to be 60 hertz, and in Turkey it's going to be 50 hertz. So it's going to be different. This reactance depends on this AC source's angular frequency, and it also depends on C, the capacitance. Okay. So that also means that if, for example, angular frequency is different in some circuit, so this is going to be different. So for a given voltage, the current in the circuit will be different. So the current in the circuit, it also depends on this angular frequency of the AC source. Okay. So now what happens to the current and the voltage in AC circuits? So in AC circuits, the voltage and the current on the capacitor are not in phase. Okay, they are out of phase. The voltage on the capacitor, it lags behind. Remember, I used this word just a couple slides ago with sine waves. So here you go. The voltage lags behind. It means comes after in time the current by 90 degrees. So you have to learn this. Okay, you have to memorize this. If you take advanced electronic circuit theory classes, you will learn why this happens. But here, you're just going to take it as granted, okay? So now look at this plot, okay? So there's current and there's voltage. So this current is the current passing through the circuit. So this shows that current. And the voltage, the red curve, it's the voltage across the capacitor, okay? This is the voltage. Now look at who's behind, who's coming behind, okay? Now the current, be careful here, the current becomes maximum first at time pi over 2, and the voltage becomes maximum later, right? After time passes, how much time, well, actually it's frequency times time, after pi over 2. So the voltage comes later, right? That's why we say the voltage on a capacitor lags behind the current by 90 degrees. You can see that here, the difference in phase between the voltage and the current is 90 degrees, or pi over 2 radians. Now, what we learned before is, okay, by the way, so what is the formula for these plots? Now let's think about it. So in this chapter, we're going to take current always as this. So it's going to be some maximum value, this value, and it's multiplied by sine omega t. You may ask, could it be cosine? Yes, it could be cosine, but let's just use sine. Okay, so, and you know, cosine and sine, basically they're the same functions, except there's a phase difference of 90 degrees between them. Anyway, that's not very important here. So for the current, we're going to always use this. So now you remember that the voltage can be in phase with the current or out of phase. So we're going to write the phase here. Okay, so here it says the voltage lags behind the current by 90 degrees. So if this is the current, then lagging behind, coming after by 90 degrees means you add a negative pi over 2 here. Okay, the voltage is coming behind the current. Now, you can look at the sine waves plot to find the difference between in phase. But again, what we learned previously was the phasor diagrams. They are actually easier to use, easier than looking at the sine waves, right? Because it could be complicated with the waves. But if you look at the vectors, it's easier. Now look at let's say the current is here. By the way, this is just a arbitrary point angle at time. So I could show it like this. Okay, I could show it like this here. So let's say this is always rotating. Okay, both of them keeping their 90 degrees between them. They are rotating. So it's, let's say some time passes. So this rotates here, and the blue one will rotate here. Okay, and there's going to be 90 degrees between them. Okay, this 90 degrees never changes because it's actually this 90 degrees. It's the lag, it's the phase difference between them. So what I was saying is, instead of looking at the waves here, we can actually look at the phasor diagram. And how would you show it? So let's say pick some vector for the current. Let's say this one, blue one. So the voltage it's going to come 90 degrees behind the current. So you have to draw the voltage here behind the current. Behind means, when you think about the rotation in this way, the counterclockwise, behind means behind with respect to this rotation direction. So the blue one is in the front now, the yellow one is behind it, because both of them are rotating in the counterclockwise direction while keeping the 90 degrees between them. Okay. Now, if you remember with the resistors, there was 0 degrees between them. They were in phase. But if you have a capacitor in the circuit, then the phase difference between the current in the circuit and the voltage on the capacitor, it becomes 90 degrees. Okay, so what it means is basically, again, if this AC source is providing some current, so this is the current coming from the AC source, the blue curve. The voltage on the capacitor, it doesn't have to raise and increase and decrease just like this current. There is actually some lag. The voltage increases and decreases after some time the current increases and decreases. Okay, so there is a phase difference between the voltage and the current. Let's continue. Okay, so this is example 24.6 from the book. So let's say a capacitor with capacitance 34 microfarad is connected to an AC source. So again, we have a circuit with AC source and a capacitor. And the frequency of the AC source is 60 Hertz. To find omega, again, remember you have to multiply this by 2 pi. So at a given time, the current is, so at some time, the current is 0.95 amperes, and it's increasing. Okay, so you measure the current here, 0.95 amperes, and it keeps increasing. Now the maximum current is given, it's 1.45. Okay, it's going to increase to 1.45. Now the question is, what is the voltage across the capacitor? If you measure with voltmeter, the voltage here, what's going to be that? Okay, it's not asking the maximum voltage, it's asking the voltage at the time when the current is 0.95 amperes. Okay, for current to be positive and increasing at a given time, it should be in the position as shown in the phasor diagram. Okay, look at the current. Because this is rotating counterclockwise, the current is now positive. Okay. Okay. The current is now positive because if you look at the y-axis, you will see that it's the y component of the current is positive, and as the phasors rotate counterclockwise, the y component will increase, right? So if it was like, let's say, if the current was like this, it will be positive. Yes, the y component will be positive, but because it's rotating, the y component will be decreasing. But here it says the current is this much, a positive number, and it's increasing. So it should be definitely in the first quadrant here. Okay, now if you draw the current like this, now we'll learn, because this is a capacitor circuit, the capacitor phasor should be 90 degrees behind the current. So you should draw the capacitor phasor like this. Okay, so now we have the phasor diagram. So always start with taking the current, as I said in the previous slide, as some I max times sine omega t, and this omega t is, you can write it as the angle, right? So this angle is omega t. The angle depends on t, of course, because it's rotating with angular speed omega in counterclockwise direction. Okay, I can write it as in terms of theta as well. Now, what is the theta at this given time? So it's basically, if you solve for sine theta, it's going to be I divided by I max. Okay, I divided by I max. And if you invert it, so you can find theta as inverse sine or arc sine, I divided by I max. So I is given to be 0.95 at that moment. The maximum is given as 1.45 amperes. And if you make this calculation, you're going to find the angle is 40.9. It's this theta angle. So at the time the current is 0.95 amperes, the angle, this angle here, is 40.9 degrees. I suggest that you guys make these calculations with your calculator, because you have to make sure that if your calculator is set to degrees or radians, you have to, if you are finding the same number 40.9, that means your calculator is set to degrees. You can of course change that setting. Okay, so I found the angle. Now I can calculate the maximum voltage. So I'm going to multiply maximum current by the capacitance reactance. Okay, and it's going to be, and if you remember, the formula is 1 over omega times c, and omega is 2 pi f, the frequency. That f frequency is actually here 60 Hertz. Okay, so I max here, and this reactance is here, omega times C. Omega is 2 pi, frequency, which is 60, and capacitor is 35 microfarad. So 35, I have to convert it to farad, so micro means 10 to the negative 6, and maximum voltage is here. If you make the calculation, you will find the maximum voltage is 113 volts. Okay, so the maximum voltage is, you can think of the amplitude or the length of this vector. So it's 113 volts. This is the maximum. But at this time, we are looking for the Y component, right? It's going to be the voltage on the capacitor. What is that Y component? This is not going to be 110, 113. It's going to be a smaller number. How do you find it? Well, if you know the angle, you can find it, right? Or you can find it from the formula. Okay, so the voltage on the capacitor lags the current by 90 degrees that I showed you before. So the formula is this. If the current is sine omega t, then the voltage is, there's going to be 90 degrees. Okay, so we know Vmax, it's 110. And we know the theta, 40.9 degrees that we calculated. And if you use your calculator, calculate this, and you will find negative 85.4 volts. Well, it makes sense. We found a negative number, and it makes sense. This is a negative number here. So this number is the voltage on the capacitor at that time. See, it's not the maximum voltage. At that time, it's not maximum yet. The maximum is 113 volts. Now, you can find this voltage at that time also geometrically here, right? If this angle is theta, from geometry, this angle is also theta, okay? Okay, so this theta, you know this theta, so you know this hypotenuse, it's 113. If you want to find here, you can use cosine, right? So the number here divided by 113, it's going to be equal to cosine of this angle, which is 40.9 degrees. And from that equation, you can easily find also this number. So this is how we use phasors. It will be hard to use waves themselves to solve this problem. So phasors are basically, they're just making it easier, making the problems, solving the problems easier. Okay, let's continue. Okay, so let's talk about power. Okay, power at any time is given by voltage times current. We learned this when we did circuits, if you remember. This is really general. It's not, the formula is not specific to this chapter. It's general. Voltage times current. Okay, so the current is this, as always, I max times sine omega t. Now the voltage in capacitor circuits is, there's a 90 degrees lag, so it's going to be this. So let's calculate the power. So I'm going to multiply this voltage here and the current here. So there's going to be these numbers, I max and V max here, I max and V max. And I'm going to multiply sine omega t and sine omega t minus pi over 2. It's here. So if you use some trigonometry, I'm not going to go into the details, but it's easy. You can see, you can find the formulas online. You can actually write this term, multiplication of sines with phase difference pi over 2. You can write it as negative 1 over 2 sine 2 omega t. Okay, let's plot now the power. Okay, so if you plot the power, it's the gray dashed line here. See, the power changes all the time. Now it's actually oscillating twice as fast as the waves. Now look, the blue wave, it has some frequency, right? And the red one, it has exactly the same frequency as the blue one. But if you look at the power, it's actually oscillating twice as fast as the other ones. And you can see it here. There's actually, the frequency is, you can see that this is the total frequency now, 2 omega. It's actually twice as large as omega. That's why. Okay. Now, this is the formula. Okay. This is the formula for power. Now, the question is this capacitor is using that power? If we take a time average, yes, at sometimes the power becomes negative. That means the capacitor is not using it. The capacitor is actually giving out, it's delivering power to the circuit. When the power is positive, that means the capacitor is using the power. It's taking power or energy from the circuit. But it becomes negative, positive, negative, positive. Okay? So what does that mean? If I take the average, on average, is the power, what happens to the power? So let's read here. The capacitor is discharging between omega t, 0. I can plot as just t or omega t, it doesn't matter. So between 0 here and pi over 2, the capacitor is discharging. How do I know it? Because you can see that the magnitude of voltage on the capacitor at this time interval is decreasing. Now look at the voltage from 0 to pi over 2. The voltage is decreasing. Its magnitude, well, it's going from negative to 0, but what I mean is the magnitude. The magnitude of the voltage is decreasing. So the voltage of the capacitor is decreasing. That means it's discharging. Okay, so between 0 and pi over 2, it's discharging. So that means it delivers energy to the AC source or the circuit. So when the capacitor is discharging the circuit, it actually gives energy, gives current to the circuit or the generator. So the power is negative. The capacitor is not using power. It's actually giving some of the energy that it has to the circuit or to the generator or to the AC source. So that means the power is negative, and you can see that here power is negative. Now the capacitor, now let's look at the time interval between pi over 2 and pi. Let's look at this interval. You can see that the power, the dash gray curve, is positive. Okay, so at this point the capacitor is charging between pi over 2 and pi. How do I know it charges? Because if you look at this period, the voltage on the capacitor is increasing. That means the capacitor is charging. So to charge, to be able to charge, it should draw energy. It should take energy from the circuit. So it draws energy from the AC source. So the power consumption by the capacitor is positive. So if power is positive, that means the capacitor is using power. That's the definition. If the power is negative, that means the capacitor is actually giving power to the circuit. So since there's no resistor in the circuit, there's no power lost into heat or light. There's no light bulb in the circuit. It's not really, it's not wasting the energy into heat or light. It's just a capacitor. Thus, a capacitor in an AC circuit consumes zero net energy when averaged out over time. This is important. When averaged out over time. Yes, at some point it uses power. So here it gives power to the circuit. Here it uses power, gives power to the circuit, uses power. But it's basically giving and taking the same energy to the circuit back and forth. When you think about the average over time, it's actually not using any power, so the net power use is 0. Okay, so that means if you connect the capacitor to the circuit, it's not going to use up energy. If you connect the resistors, yes, it will use up energy, but for capacitors, it's not going to use up any energy. Okay. So now let's move to the next section, which is RC circuits. That means we are going to have both in the AC circuit, both the resistor and the capacitor. So we're going to have both of them. Okay, so in an RC circuit, the voltage across the resistor, we're going to call it VR. So it's the voltage across the resistor. And the voltage across the capacitor, we're going to call it VC. They are not in phase. Okay, they are not in phase. That means the VC and the VR, they're not going to increase and decrease at the same time. There's going to be some phase difference between them. So if they're not in phase basically means VR and VC reach their maximum and minimum at different times. This means the total voltage between points A and B, this is point A, this is point B. So the total voltage, if this was a DC current, you would do VC plus VR, right? You would just, because these are in series, if they're in series, you would just add them up, right? You would say VR plus VC. It will be the voltage between A and B if it was a DC circuit. But this is an AC circuit. So in AC circuits, the total voltage between A and B is not equal to arithmetic sum of VR and VC. So it's not an arithmetic sum like this. You cannot do this. This is wrong. This is not going to give you the voltage between A and B. In AC circuits, VR and VC are vectors. You can think of them as vectors, the phasors, right? The phase vectors, because these are waves. So we should do a vector sum. Now we're going to use the phasors diagrams to find the total voltage between A and B. Again, we cannot do VR plus VC because these are vectors. Now, let's look at the current. First of all, let's always start with the current, okay? Let's say the current is at a given time in this direction. So now we learned first, the first thing that we learned, the voltage on the resistor and the current, they would have 0 degrees between them. So they would be in the same direction. Next, what we learned was the voltage on the capacitor, VC, it will be 90 degrees behind the current. So it's 90 degrees here. Now, look at this, the yellow one. So the yellow vector, this one, and the red vector. Red one is for the capacitor voltage, and the yellow one is the voltage on the resistor. So now we are going to add them up. Again, it's not arithmetic sum, it's a vectoral sum. How do you add these two vectors? Well, you learned this before in physics 1. You can basically, it's going to be this vector. How do you find this, the length of this? It's basically, you can use Pythagorean theorem. So it's going to be square root VR squared plus VC squared. You can calculate it that way. And you can find the angle between, so any angle, either this one or that one, by using these lengths, hypotenuse, and sine or cosine. And we're going to do some examples on that. So after this point, it's just geometry or vector addition. Okay, let's continue. So the goal here is first find the total voltage. We're just continuing the same problem. Between points A and B, what is the total voltage between A and B? Then find the current Imax in the circuit. So what is the current passing through the circuit? We can find the RMS values or the maximum values. By the way, I'm not really talking about the current passing through the capacitor or the resistors because these are in series, right? So the same current will pass through each one. That's why when I talk about current, I always talk about the current passing through the circuit because it's the same current. But of course, the voltages are the same because they are in series. Okay. So we are going to find the maximum voltage between A and B from the phasor diagram. Okay, so as I explained, start with the current, the green one, and the voltage and the current will be in the same direction. The voltage on R, the resistor, they're going to be in the same direction, and the voltage on the capacitor, it lags the current by 90 degrees, so it's going to be behind the current by 90 degrees. This is 90 degrees. So after you know these, now what is the maximum current? We can calculate it from here, basically using Pythagorean theorem. Now what is VR max? It's basically I max times R, just Ohm's law. So whatever current passes through here, if I want to find the voltage here, it's going to be I times R, either RMS or you can use maximum. If you use RMS, it's going to give you VRMS. If you use max, it's going to give you Vmax. Okay. So this is the current. Okay, how do I find, sorry, this is the voltage. How do I find the voltage on the capacitor? If you remember, we had a formula that looked like Ohm's law, but so we had I times the capacitive reactance. Okay, that's how we write it. We learned this in the previous slides. Now, how do you find from this triangle, if you look at these two vectors? So this I max times R, if you like, you can move it here. This is VR max. I'm going to put just M. So if you look at this triangle, if you want to find the hypotenuse, which is the maximum value of the current between A and B, you are going to do this squared, VR squared maximum, VC maximum squared, square root 2. And in fact, that's what we are doing here. Okay, so I have I max squared here, also I max squared here. I can use a common parenthesis, so I can basically have the I maxes here, I max squared, and I can take I max squared outside the square root 2, so it's going to come out as I max here. So what's left inside the square root 2 is basically R squared coming from this term, and xc squared here. Now we're going to have another term here. This thing, okay, this whole thing is called impedance. Okay, I'm going to explain what it means, where that word impedance coming from. It means it's coming from the word impede. Okay, try to stop or the react, or like this is the response of the circuit to the AC source. Okay, it's called impedance. So, and if you look at it, it looks like Ohm's law, right? So if you had on the capacitor, we had I max times, it's actually here, I max times XC. If you have on this capacitor, I max times the capacitive reactance. If you have only R, it's basically Ohm's law, I times R. But if you have both of them, R and C in the circuit, this combination, it's called the impedance. Okay? And it just looks like Ohm's law. You can use it with maximum values of the current and the voltage, or RMS values of the current and voltage. Okay, let's move to the next slide. Now, impedance, let's think about this word. Impedance is generalization of resistance, because it just looks like Ohm's law, right? And like resistance, impedance determines how much current will flow in the RC circuit with AC source. This term impedance here, Z, by the way, it only happens in AC circuits. We don't talk about impedance in DC circuits. Okay? So impedance coming from the word impede, if you look at the dictionary, it's to retard in movement, to retard, so basically introduce time lag You do something, and if there's impedance, it reacts to the input at a later time, okay, to retard in movement or progress by means of obstacles or hindrances. It also means obstruct or hinder. Okay. So why do we use this term? Because remember, when the AC source gives some current to the circuit, but the circuit itself here, RC circuit, it doesn't react immediately. The voltage, for example, on them doesn't increase immediately. So there's a time lag. So there is some impedance. So that's the circuit is, there is some retardation or lagging in the circuit. That's why the value that you calculate from here, it's called impedance. This is the same formula that you saw in the previous slide. Okay, now this, we call this Z impedance, so it's here. And again, this is just a reminder here, capacitive reactance is shown as 1 over omega C. Okay, if you want to calculate impedance with RC circuits, you will use this one. Now I can ask you, what is the impedance if you only have R? Well, it's just R, because it's Ohm's law, right? V equals IR. What is the impedance if you have only capacitor? Well, it's actually this guy here. It's going to be XC, and you can see it here. What is the impedance if you have both R and C? Then it becomes this formula. Okay, let's continue. Now we are continuing with AC circuits. Again, now in this slide, I'm going to teach you what happens, like how can you combine two waves? And you're going to understand why do we need phasors. Okay, now if you want to, let's say again you have an RC circuit, you want to calculate what is the voltage between A and B. If this was a DC circuit, what you would do is you would add the voltage here, VR, plus voltage here, VC, right? But you cannot really add, if this is because this is an AC circuit, you cannot really add the voltages. The reason is, now the voltages are actually waves. They're not constant. So look at this. Maybe the voltage here is like this, and the voltage here is like this. They are not becoming positive and negative at the same time. They're different. There is a phase difference between them, right? They're not the same. So you cannot really add them up arithmetically. Okay? So the question is again, what is the total voltage between A and B? Since voltages are waves, VAB is not equal to VR plus VC, so that will be wrong. To find VAB, we need to use phasors. Now here, the phases are here, okay, the vectors. Now I'm going to show you, this is an animation that I made in Mathematica. This subject is not really explained well in the book, so I hope you're going to understand it here. This is basically, now I'm going to teach you about waves, how you add waves, what happens if you add waves when there's a phase difference between them. Okay, now so let's okay, so I'm going to play this now. So what we have here is we have two waves, the black and the gray. Okay, let's say this is voltage 1, the other one is, let's say, voltage 2. Okay, and the orange one is basically the addition of these two voltages. So see here, the voltages, they have different amplitudes. So one of them is, the gray one has actually more amplitude. But at this moment, you can see that they are in phase. They become 0 at 0 time, at time equals 0. They become maximum at pi over 2. They become 0 again at pi. So they are in phase. Okay, their frequency is the same, and their phase, they are also in phase. Now look at here, it says at this moment the phase difference is 0 pi. So it's basically zero radians or degrees between them. Okay, now here you can see that. Now look at the two vectors, the gray and the black. At this moment, the phase difference is between them is 0. You can see that they are in the same direction, and you can basically add them up, right? So here, this plus this, it gives you the total, the combination of VR and V2. Now I'm going to play it. What happens is, so you're going to see that. Now the gray is picking up some phase. The gray is moving forward, okay? So now look at the total. Now you can see that, so the black one is constant. The gray is picking up some phase. It's actually now it's now lagging the black one, right? It's coming behind the black one. And you can see that it's behind now the black one. And now the summation is the vector sum. You can see that here. And here you can also see the summation is moving. And it's actually decreasing, right? The summation is decreasing. You can also see here the vector here initially was longer, now it becomes smaller. And as the phase grows, now at this moment the phase difference is pi over 2. You can see that it is actually 90 degrees between two, right? The phase difference between them is pi over 2. And the addition of them is shown with this vector, and the length of this vector is actually the maximum value of the orange wave here. Now let's continue until the phase difference is pi. Now I'm going to stop here. Now the phase difference is pi. Look at the black one. It's not, the drawing is not perfect, but maybe I'm going to move it a little bit. Okay, maybe a little bit back. Okay. Now the phase difference between them is pi. You can see from the vectors, right? There's a pi or 180 degrees between them. Now look at this one. The black was stationary, and this curve moved forward, right? Now you can see that the black one becomes maximum at pi over 2, and the gray one becomes maximum at 3 pi divided by 2. So there's a phase difference of pi. It's also shown here. Now look at the maximum voltage, the combination of them becomes really, really small, right? Look at this orange orange vector here. It's small. And if you look at the sine waves, the maximum value of the orange wave becomes small. Okay, let's play it again. Now they are in phase, 0 degrees between them. The amplitude, the total or the combination is maximum, and it's going to decrease as the phase difference grows. You can look at the phase difference here, and you can verify it from the phasor diagrams as well. Let's play it again. Okay, just like that. Okay, so I would like you guys to stop here to understand, play the video back and forth and understand the relationship between the waves and the phasors, phase vectors, okay? And you should now understand at this point why we cannot simply do VR plus VC. Because when they are not in phase, the addition has to be vectoral addition. You can see it from the phasors, or you can see it from the waves here. By the way, how do you add them up? How do you add waves in this plot? Well, basically, now look at here. At this point, if this is, let's say, 5, if this is 6, then you would add them up. It will be 5 plus 6, it will be 11, right? But if it moves forward, let's move another time. Actually, let's move to the phase difference when it's pi. Okay, let's look at here. Now, let's add them up. Let's add the gray one and the black one. So if the gray one is like 6, if the black one is like 5, well, it's going to be -5, so it will be just 1. See, the addition will be a small number, just like 1. And the same thing here, if this is 5, the black one is 5, if the gray one is 6, then the addition will be a small number to the left, small vector to the left, which is 1. This is why you cannot simply add these numbers up, okay? Now you are actually learning a lot in this slide with this animation. It's not just AC circuits, but now you're learning how the waves get together, what is the phase angle, how they relate to the phasor diagrams. Okay, this, if you understand this, I would say you are now starting to get a good engineer. Okay, I'm going to continue. Now let's solve this problem related to AC circuits. So we have, let's say, so in this problem everything is given in the figure. So we have the RMS voltage, we have the frequency, and also the current in the circuit is given, the RMS value of the current, and the capacitance is given. The question is asking what is the resistor, what is the resistance of the resistor in the circuit. Okay, so now what I can do is I can use something, this formula, which again looks like Ohm's law, okay? And in fact, the units of Z, the impedance, is actually ohms, just like resistance. And I'm going to use this. The impedance is the whole thing, right? Not just resistance, but the combination of these two. So, and I can rewrite this equation as impedance equals V divided by I. The voltage, RMS voltage, is 120, and the current is given 2.5. Okay, if you divide them, if you do this division, you're going to find the impedance Z is 48 ohms. Now, what we are trying to find is R, right? So now I'm going to use this equation. So I know Z, I calculated it, and I can know what XC, because C is given and the frequency is given, so I can also find this. So from this equation I can find R. So I'm going to solve this for R. If you take the square of both sides and do the manipulations, you can find R is given by square root 2 impedance squared minus capacitive reactance squared. What is the formula for capacitive reactance? It's 1 divided by omega C. Don't forget the square here. Okay, if you plug in the numbers, we calculated this, and everything else is given in the problem. So the frequency is 60, and omega is, remember, don't forget the 2 pi. It's 2 pi f, right? 2 pi frequency. And also don't forget to convert microfarad to farad. So micro means 10 to the negative 6. And if you do the calculation, you will find the resistance is 47 ohms. Okay, let's move on. Now, we're going to talk about power with RC circuits. Remember, if you have circuit with only resistance, the power is I times V times I. If you have capacitor, the average power would be 0. We talked about this. But if you have RC circuit, of course, because of the R, the circuit will consume some power. So there is this concept, it's called phase angle between the Vmax and Imax. Now here, phi is not the phase angle between the current and the voltage. It's 90 degrees in RC circuits, but it's something else. It's a new concept. It's the angle between, shown with phi, it's the angle between the maximum voltage here and the current. So it's this angle. Okay, so cosine of that angle is called power factor. And it turns out it's actually R divided by Z. R divided by impedance. Okay, average power is given by RC circuit, okay, when it's connected to AC current. So it's basically, again, the same formula. This part is the same, I squared R. And so here we can rewrite it as I times V times cosine theta. So this is the power. This is the power factor. Okay, so the average power for our circuit. So when there's only resistor in the circuit, what is the average power? So the phasor of the voltage and the current are in the same direction. Now look at the current and look at the phasor of the resistor. They are in the same direction. What is the phase angle between them? Well, 0. Okay, then this cosine 0, it's also here. Cosine phi, it's going to be cosine 0. So this is going to be 1. So the power will be I times V. Of course, you have to use the RMS values. So the power consumption is actually maximum. Why is it called maximum for our circuit? Well, you can see that what is the maximum value that a cosine can take? Well, it's 1. And in fact, it's here taking the value. It's becoming 1. So the power consumption power becomes maximum. Any angle that you use other than 0, it will give you, the cosine of that angle will give you something less than 1. That's why here it's maximum. Now so this was only for circuits with R. What about the circuits with only C? Okay. Now the most general one here, it was the RC circuit. So to calculate power, we would use this one. Now we are looking at the special cases. Now first we look at the special case where there is no C, no capacitor. Now we're going to look at the second special case where there is no resistance but only capacitor. So the average power for capacitor circuit, for only a capacitor, the phase angle between the maximum voltage and the current is 90 degrees. Remember, there was a 90 degrees lag. So, and cosine 90 degrees is 0. So the average power is 0. In fact, we found this before, right, when we talked about the capacitor circuit. So the AC circuit with only capacitors, no resistors or inductors, we're going to come to them, they don't consume power. This makes sense because the capacitor is just getting charge and discharge constantly. So it's not a resistor to cause heat dissipation. So there's no really heat dissipation or in the form of, so it's not, because there's no resistor, so the average power is 0. We talked about this before actually. And we also verified what we know from this formula, because in capacitor circuit, this angle becomes 90 and cosine 90 is 0. Okay, so let's continue. Let's look at this example. So which light bulb shines more brightly? What is the difference between them? Well, they are connected to AC sources, except the second circuit has an extra capacitor. So the power will be again like this. Okay, current times voltage times the phase angle between the maximum voltage in the circuit and the current. And the current can be written as the voltage divided by impedance. Again, look at this. This is just like Ohm's law. And the impedance in RC circuits will be R squared divided by R squared plus XC squared in the denominator. This one is, we're going to use it for this one. For this one, for this one, I is just, for circuit 1, I is just V divided by R. Okay, what is the power consumed by the light bulb or the resistor? Basically, light bulbs are resistors in circuit 1. Well, it's going to be the current squared, which is V divided by R squared times R. This is the power. What about the power in the RC circuit, the circuit 2? It's going to be, now the current here, you can see that. The current here is now this one. So if you take the squared, it becomes V RMS squared divided by R squared plus XC squared times R. Now let's compare these two. So everything is the same, V squared R is the same in both, but this one is divided by a larger number, so this power will be smaller. So the power in the circuit 1 will be larger then. So the answer is power consumed in circuit 1 is greater when you compare it to circuit 2. So the light bulb in circuit 1 is brighter. Okay, so now we are going to continue with inductors in AC circuits. Remember, inductors were just like coils. Okay, so let's remember what happened when we connected them to DC sources. Okay, so for DC current, the inductor or coil would respond with back EMF. So by the way, these should be batteries. We're talking about DC source. Let me do this. So there's a DC circuit here. Let's remember what happened with the DC circuits. Okay. So when you connect it to a DC circuit, so there's going to be some current, right? And this this inductor will oppose that current. So it will create back EMF or back voltage or opposite voltage to oppose the current or the voltage in the circuit. For a few milliseconds, it's going to take really short amount of time, because when you connect, initially the current is zero. Right at the time when you connect it, the current will raise from 0 to some degree. If you remember, there was a plot like this. The current in the circuit, and when there's an inductor, it will raise from 0 and it would reach some constant value. It actually takes a really small time, milliseconds. When the circuit opened or closed, and once the current becomes stable, just like this point, after a couple of milliseconds, the coil would act as a straight wire, just like here. So in DC circuits, initially the coil reacts to this increase in the current, but it takes milliseconds, and after that point, the coil becomes it acts just like a wire. It's actually a wire, but because it's a coil, it can produce a magnetic field, and the change of magnetic field, the change of flux, it causes the inductor to create back EMF in the circuit. But it only takes milliseconds. After that point, it will just be like straight wire in DC circuits, okay? But with AC current, the current is constantly changing. It's not just like this, right? The current is now in AC circuits, it's back and forth. It changes direction in 1 second, maybe 50 or 60 times. So the inductor will create back EMF all the time. Remember, the inductor acts like a straight wire when the current is constant in DC circuits. But when the current changes, it also happens in DC circuits initially for a millisecond, the inductor creates a back EMF. It induces a current in the opposite direction. But after some point in DC circuits, it doesn't happen. But in AC circuits, it happens all the time. So the inductor creates back EMF all the time. Okay, so now let's relate the current. So how is current at the inductor related to its inductance L and the angular frequency omega of the current? Now we have a relation similar to Ohm's law again. So it's V equals I times XL. So remember this we had for capacitor reactance. For inductors we have inductive reactance, just like that. Now the formula for that is omega times L. L is the inductance of this inductor. So it's basically a number for that inductor. And again, this inductive reactance, it's in units of ohm. Okay, so now we talked about the current and the angle between the current and the voltage in R circuits, in C circuits, in RC circuits. Now let's talk about what happens between the current in the circuit. Okay, we have the current in the circuit and the voltage here. You can call it epsilon or V. Now the question is there a phase angle between this voltage and the current when we have an inductor in the circuit? So in AC circuits, the voltage and current in an inductor are not in phase, just like capacitors, but there's a difference here. Now, the difference here is that the voltage on an inductor now leads. It means comes before the current by 90 degrees. So again, start with the current here. Okay, now the voltage on the inductor is not behind as in the case of capacitors, but the inductor voltage now it's leading, it's in front of the current. So it's basically, that means the voltage on the inductor, see, look at here, the voltage in the inductor becomes maximum, let's say at this time, but the current becomes maximum at a later time. Okay, so the current comes behind, it lags, but the voltage, it's leading, it comes first. This is exactly opposite of the capacitors, right? And we are going to do RLC circuits where we're going to have both capacitors. We are going to have resistor, capacitor, and inductor at the same time, and you're going to see all the phases in one diagram. But the point here is the voltage on the inductor is 90 degrees. It's basically now the current is 90 degrees behind the voltage on the inductor. You can see it at the sine waves, or you can look at the phasor diagram. Okay, so now we are basically the voltage on R. Now we're going to talk about RL circuits. Okay, now the voltage on R and the voltage on the inductor here, they are at 90 degrees. Okay, there's a 90 degrees between them in the diagram. You can see in the phasor diagram. This is the current, the green one, and the blue one is the voltage on the inductor. There's a 90 degrees between them. And also because the VR, the voltage on the resistor, is also in the same direction with the current, we can also say that the voltage on the resistor and the voltage on the inductor, they also have 90 degrees between them. So if you want to find the voltage between A and B, the total voltage, again, you cannot add them up arithmetically. You cannot say VR plus VL. You have to add them vectorially, okay, not algebraically. So how do you add them up? Okay, we are going to add VR and VL. Here is VL and here is VR. Okay, if you have two vectors like this, you can actually have to carry this VR here if you want. So this is going to be VR, and this is basically VL here. Now, how do you find this hypotenuse from this triangle? Well, you're going to do VR squared, VL squared, square root 2. And this is actually what we do here. VR squared, VL squared, and square root 2. Again, so we have I max squared here, common term in the square root 2. I can take it out as I max. And again, what's left is again called impedance. So this is the impedance formula for impedance in RL circuits. Again, what you have is you can use maximum values or RMS values. This formula, which just looks like Ohm's law. Okay, like resistance, impedance determines how much current will flow in RL circuit. So the idea of impedance is the same, either whether you have RL circuit, it could be RC circuit, or we're going to see RLC circuits. Basically, impedance, you can calculate the current by using the impedance. Okay, what about power in RL circuits? There's a phase angle, it's actually, we learned about this, between the voltage and the current, as seen in the phasor diagrams. So cosine of that angle is called power factor. We learned this. Okay, it's here. Now the only difference is impedance. Now instead of 1 over omega c, we have just omega times L. So the average power in RL circuit, it's shown, the phasor diagram is here. This is the RL phasor diagram. It's basically this thing here. Okay, so there's a cosine phi, and what is that phi? It's basically the maximum voltage between remember the AB point. So the maximum voltage is the voltage on inductor plus voltage on resistor, and the angle between that maximum voltage and the current, it gives you that angle, phi angle, and if you plug it here, you can calculate the power. But what about if you have not RL but just just L? If you have L circuit, again, you have the current here, and the current is behind the voltage by 90 degrees. Now, if you plug 90 degrees for cosine here, 90 degrees, it's going to give you 0. So the power is 0 in only inductor circuits. It's just like the only capacitor circuits, right? So, and it makes sense because the inductor is charging and discharging by storing energy in terms of magnetic fields. So the capacitors, they were charging and discharging by storing, basically you can think of it as electric field inside, because you are collecting positive and negative charges in opposite plates. So you can think of capacitor as storing electric field, and you can think of coils or inductors storing magnetic fields. Remember, there is a change of flux as the current changes, so the inductors are actually storing magnetic field. But they're not really using it up, and the power becomes negative and positive all the time. And if you take the time average, the total power used by the inductor is actually 0. Of course, an ideal inductor has no resistance, so no heat is dissipated, but in real life, inductors are cables, well, coils. All coils and cables, they have some resistance, so in reality, the power will not be 0. But if you have ideal conductor, in theory, the power is 0. Let's continue. Now here, it's a similar question, just like the previous one, but here instead of capacitor, we have an inductor. Which light bulb shines more brightly? The same question. And the power is given by this formula that we learned. But of course, you need to know the current. How do you calculate current? If you have just R, so this is just R circuit. If just R, the current is given by the Ohm's law, just divided by, so V RMS here, V is here from the source, divided by R. But if you have conductor, now you have to divide it by impedance, which is combination of R of the light bulb and the reactance of the inductor. Okay, so in circuit 1, the power will be this. In circuit 2, the power also basically use these I's, this one here, and this one here, just take the squares. Okay, so this is the power for circuit 1 and this is the power for circuit 2. You can see that the circuit 2 is divided by, so everything v squared r, they're the same, but the circuit is divided by a larger number. So that means this is going to be smaller. So the circuit 1, the power in the circuit 1 will be smaller. So the answer is power consumed in circuit 1 is greater. So the light bulb in circuit 1 is brighter. Okay. So now we move to RLC circuits. Okay, they are very important circuits. So the phasor diagram, now we have all the components R and C connected to the AC source. Okay, and in reality they are like this. So this is the resistor, this is the capacitor, and this is the coil. In reality they look like this. They're simple, but they are basically, I could say, I can easily say that they are the basic building blocks of our modern technology. So the phasor diagram for RLC circuit, so again, start with the current, I times sine omega t, and the current is the same for all circuit elements, right? Because the current, they are connected in series. The current is the same in all circuit elements connected in series. Okay, but the voltages are different in magnitude and phase. The voltages will be different. So let's start with the current. So here's the current, the green one. Now the voltage on R, it's going to be I times current times R, right? But what about the phase angle? Well, the phase angle will be 0 because the voltage on R and the current in the circuit, their phasors are in the same direction. Okay, they're in phase. Now the capacitor, you know that it's 90 degrees behind the voltage. Sorry, behind the current. You can see it in the phasor diagram. And if you want to calculate the voltage here on the capacitor, we learned that it's I times the capacitor reactance. And what about the voltage on the inductor, VL? Well, we know that it's the current, so it comes 90 degrees after the current in the circuit, so it's here. Okay, and if you want to calculate the magnitude, the length of the vector, it's going to be I times inductive reactance, XL. Okay, now we have three vectors. So we have three voltages. If I want to calculate the voltage between A and B, so I'm going to look at VR. So I'm going to add VR, VL, and here VC vectorially, right? So what are those vectors? It's the light blue, it's the orange one, and it's the red one. Okay, how do I add these up? First, what I would do is I would add VC and VL because they're in the opposite direction. Well, basically I'm going to subtract them. So VL minus VC will be this purple. Okay, so this purple one will be VL minus VC. Okay, and I also have this VR, which is 90 degrees and it's in this direction. This is VR. So after this point, just again use the Pythagorean theorem to find the voltage between A and B, the total voltage. Well, if you look at here, so this one is VR. So it's squared, and The second term, the whole thing is actually, let me draw like this vector VL minus VC, and you can see that VL is I times XL minus, this is VC, I times XC. So after you draw the phasors, after that point, it's basically just geometry or just vector addition. Now you can see that Imax is common term here. It's actually Imax squared. Take it out from the squared as Imax. So what's left inside is R squared XL minus XC squared square root 2. Now this whole thing is called, again, impedance. It's in units of ohm. So this is the impedance when you have R, L, and C circuit elements in the circuit. And if you remember, XL is just omega times L, and XC is 1 over omega C. Okay, so now let's do this example. The circuit elements shown in the circuit are connected to the AC source. Again, these are just like in the previous slide, they are in series. So the voltage is 41 volts and the frequency is 75 hertz. The question is, what is the RMS voltage across the inductor? So it's basically asking VL, not the maximum value, but the question is asking RMS. Sorry, RMS. Okay, so since the circuit elements are in series, the current passing through each element is the same. It's the same current that passes through each one, but the voltages on each element is different. Of course, it should be different, right? So it's going to be V equals, for this one, I times R, for this one, I times XL, for this one, I times XC. So they will be different numbers. Also, the phases will be different. Not the amplitude, but also the phases will be different. So the total voltage between A and B is equal to the source voltage. You know that. I mean, if you have 41 volts here, remember, this 41 volts is parallel to the whole thing between A and B. Okay, so the voltage AB is the RMS values, so is 41 volts. Okay, now the total impedance, what about the total impedance? It's this formula that we found in the previous slide. Again, don't forget 2 pi f. So what's given here is f, not omega. To find omega, you have to multiply it by 2 pi. Now, we know everything here in this equation, so plug all the numbers and calculate the impedance. It's impedance 43 ohms. So impedance basically means the effect of all of these is 43 ohms. Okay, it's the impedance. Now, let's find the current. Now, the current between A and B, so the voltage between A and B will be the current in the circuit times the total impedance, or the current will be the voltage divided by the total voltage between A and B, which is going to be 41 because these are parallel, 41, divided by the total impedance of the circuit, which we found 43. If you do this division, you find the RMS current is 0.95 amperes. Now, this current is actually going through all the circuit elements. It's the same for all. Even though we calculated that current from the whole circuit, but it's also the current that passes through each element, right? Okay, so if I know the current here, if I multiply by, so I know the current, if I multiply by XL here, it's going to give me the voltage, right? So that's what I'm going to do here. VRMS L will be the current RMS times the inductive reactance XC, and inductive reactance is omega times L. Okay, so I am RMS current is 0.95 here, The omega here is 2 pi 75. Why 75? Because it's 75 hertz. That's the frequency. I have to multiply by 2 pi. And the inductance is 150. It's given in the problem. So 150 millihenry. So milli means 10 to the negative 3. I have to convert it to Henry. And if you do the multiplication, you will find the voltage on the inductor, the RMS voltage, is 67 volts. Okay, let's continue. So in this table, this is basically a summary. What happens to the impedance when you have only R? Well, it's just R. Only capacitor, it's this formula. Only inductor, this formula. What happens if it's a RC circuit? This is the impedance. RL circuit, and finally RLC circuit. So you have the impedance formulas. Okay, so resistor is also impedance. So in AC circuits, everything is in terms of impedance. And in this table, it's basically the power. You can notice that if you have only C or only L, inductor or capacitor, the power is, we discussed this, becomes 0. So basically, what consumes power is when you have a resistor in the circuit. And here is the summary of the phase angles. And if you want to find the phasor diagrams, you can look at the slides, previous slides, or you can look at the figures in the book. I said this a couple times. I will say it one more time. The total current, look at this circuit. The total current between total voltage between A and B is not the summation of the voltages. Okay, you have to do a vector sum because the phases are not the same. So you have to find the vector sum. So basically you have to use the phasor diagrams. Okay. Now I'm going to discuss one more thing in RLC circuits. So what happens at the very high frequency or very low frequency? Let's say you have some voltage source. What happens if the frequency of the AC source is really, really small or really, really high? In this case, we don't have everything, so these are RLC circuits, but they're not necessarily in series. Here, L and the resistor, this resistor, they are in series, but they are parallel to C and R here on the side. So let's think about what happens. So this is the circuit, okay? If the AC source is if there's high frequency, let's say I turn the knob and I increase the frequency here, frequency F, what happens? Now, in the high frequency limit, so limit basically means you give to the surface really, really high frequency. It's almost like the frequency goes to infinity. Think about it, calculus. When you take the limit, it's like high frequency limit means you're taking the limit as the frequency goes to infinity. Okay, so that means high frequency means rapid change in current. Okay, because it's high frequency, and that means this inductor, because the inductor doesn't like change. If there's change of current, it basically produces back EMF, so it tries to stop the change in current, so it produces current in the opposite direction. So very large, it will produce very large back EMF because it's sensitive to the change in current, not the current itself, but the change in current. So the inductor coil will not let the current pass. So it will act as a broken wire. So this inductor, it's not going to let the current flow. So it's going to act as a broken wire. What about the capacitor? Well, if there's a high frequency, then the capacitor will always charge and discharge without completely charging, since the current changes direction fast. If the capacitor charges completely, it doesn't let the current pass. But in high frequency limit, because the current changes so frequently back and forth, the capacitor never gets charged. And because it never gets charged, then it basically acts, it always lets the current flow through it. So it acts as a straight wire. So the capacitor is acting as a straight wire. So then look at the circuit. What happens is now this part is gone. So that circuit, this original circuit in the high frequency limit, it becomes just as an AC source and this this resistor 240 ohms resistors. Now let's look at the low frequency limit. Again, remember from the calculus, it's like taking the limit of the frequency as it goes to 0. Okay. Now, because the current now changes really small, the change in current is really small, the frequency is small. Now remember, inductor doesn't like change, but the change is really small, so it will actually let the current flow. So it will act as a straight wire, inductor. So very small back EMF, inductor coil will let the current pass, so it will act as a straight wire. What about the capacitor? At low frequency, the capacitor will be charged before the current changes direction. Because the frequency is so low, the current doesn't change its direction frequently. And before the current flips in the opposite direction, the capacitor will already get charged. So then it means when the capacitor is charged, it acts as a broken wire. It won't let the current pass. So the capacitor acts as a broken wire. Now what happens to this circuit? Now this part is gone. So at the low frequency limit, the circuit becomes AC source and a resistor, but this time this resistor, which is 120 ohms. So this is the original circuit, but its high frequency and low frequency limits are different. So how is this relevant? Well, if you have, let's say, a sound system, and if you want to filter out some of the frequencies, let's say maybe low frequencies or high frequencies or some noise at some particular frequency, then you would use circuits like this to filter out the sound or the voice or the noise at a particular frequency or low or high frequencies. So this is actually, we have circuits like this in a lot of sound devices like recorders or players. Okay, now let's talk about the concept resonance. This is, so I mentioned, if you want to be an engineer or a scientist, it's one of the concepts that is really important is the waves and the phases of the waves, how you add them up. The second concept is really important, is resonance. Okay, so now I'm going to talk about resonance, but before that, let's talk about the from physics 1, the spring and the box system. So the box has mass m. Let me write it here. Box mass m. There's a spring constant k from Hooke's law, if you remember. So this is going to go back and forth, and the frequency, the angular frequency actually in this case, will be k divided by m with the square root. So if you change k, let's say if you use stronger spring, it's going to go back and forth more quickly, right? The oscillation will be more quickly because the frequency will be more. If you use more massive box, the frequency will be low, smaller frequency. But anyway, so there is some characteristic frequency for a system in terms of the constants of the system. If you have a pendulum, so a pendulum is something like this. It oscillates left and right. Okay, it's a pendulum. It's hang on the ceiling. So now the angular frequency, like what is the frequency of going back and forth, it would depend on the gravity G, and it would depend on this length of the rod L or the rope. Okay, these are the angular frequencies, the characteristic frequencies in mechanical systems. Now, let's come to the circuits. If you have an LC circuit, no resistor, okay, just L and C, the capacitors. So this one is the capacitor, this one is the inductor or coil. Now the characteristic frequency becomes 1 square root 1 divided by inductance times capacitance. Okay, this is the characteristic angular frequency. This is the angular frequency of this circuit. So what happens is, just like oscillations in the mechanical systems, there is an oscillation in the circuit. So let's say initially the capacitor is charged and you close the circuit, you close the switch. Now the current flows from positive direction, from positive terminal to the negative terminal. Capacitor is just like battery, right? Now, because there is current flowing, so it starts from 0 and increases. Now, because it increases, now this inductor, it doesn't like the change in current, remember? So it's going to react to that. So it will try to create current in the induced current in the opposite direction. In the meantime, it will have magnetic field lines inside, right? So it's basically now the capacitor will be discharging. It will be discharged. So where's that energy going to? Well, that energy going into, it's gonna, now the energy is stored in the inductor, in the coil, as magnetic fields, in terms of magnetic fields. In the capacitor, initially the energy was stored in terms of electric fields. Now it got discharged. Now the energy is stored in the inductor in terms of magnetic field lines. Again, after some point, this, now it's going to it's going to create its own. We know that as a back EMF, it creates back EMF. Okay, so back EMF is like basically the inductor itself acts as a battery in the opposite direction. If it acts as a battery, now it will start to charge the capacitor, right? So what happens is the capacitor is discharging, it's charging the inductor, and then the inductor charges the capacitor back, and this happens back and forth continuously. Because there's no resistor in the circuit, there's not going to be heat wasted or energy wasted. So this is going to happen back and forth all the time if you have an LC circuit. Now, what is the frequency of that, discharging and charging? What is that frequency? Again, it's given by this number, LC. Sorry, square root 1 over LC. So that means if, let's say, if you increase L, then the frequency will go down. So if you use an inductor and capacitance with small l and c numbers, then small number divided by small numbers, 1 divided by small numbers, it will give you a large frequency. So small inductance and capacitance will give you a faster frequency. Okay, so it's going to, current will go back and forth faster in that case. Okay, let's see this example. By the way, these circuits are related to radios. Now you will see how it's relevant, also the concept of resonance. So you want to make a radio that plays FM 88.5 megahertz. You know that different radios, they play at, they broadcast at different frequencies. But let's say you want to listen to this particular radio at that broadcasts at 88.5 megahertz. What do? Well, you need a circuit, you need an LC circuit, just like these, which matches, of which characteristic frequency matches the frequency of the radio that broadcasts at this frequency. Okay, so the inductor that you're going to use is, its inductance is 1.5 microhenry. What should be the capacitance of the capacitor? Well, what you want is your circuit, the frequency of your circuit, to be exactly this number, the frequency of the radio channel, so that you can listen to that channel. Not any other channel, but that particular channel. Well, then you want the angular frequency of your circuit to be exactly 88.5. Okay, now what we don't know is C here. If you pull C here, if you solve for C, it's going to be 1 divided by omega 0 squared L. Now I want this omega 0 to be 88.5, so it's going to be, well, this is the frequency. I have to multiply by 2 pi. And so this is megahertz. Mega means million, okay? So it's 10 to the 6. Notice that it's 10 to the positive 6 mega. And there's a square here, and the inductance is given in the problem. It's this. So to get this frequency, then you have to use this. You have to use your capacitance should be this one, so that you can listen to this radio. Okay. So now, so I talked about pendulums. Pendulums are like swings, or swings are like pendulums, right? Now, I am sure that you experience this. If you push someone on the swing at natural frequency, so there's a particular frequency that you have to push the person, so let me read here. You push someone on the swing at the natural frequency of the swing. Let's call it omega 0. Let me go back. So it will be gravity G divided by the length of the swing, square root. Okay, let me go forward. And the speed of the swing increases. Okay, and this is resonance exactly. If you push someone on the swing with the frequency that matches the natural frequency or the characteristic frequency of the swing, then the speed of the swing increases. This is called resonance. But if you push at a lower or higher frequency, you can try this, okay? The speed of the swing decreases, and the swing eventually stops. So you can try this. You can try pushing someone with a really small frequency, like push that person with small frequency. You will see that it's not going to work. If you try to push the person with a high frequency, you know that you're going to see that it's not going to work. So you have to push the person exactly at that natural frequency or characteristic frequency of the swing, so that the speed increases. Now let's come to RLC circuits. The current that the RLC circuit draws from the AC circuit, so the RLC circuit, it will draw the current, it will draw some current from the source, right? It will take some current. So it becomes maximum when the frequency of the AC source, omega, this one, the frequency of the AC source, is equal or around the natural frequency of the RLC circuit, omega 0. So what this is saying is, this RLC circuit, it has some particular frequency, right? So R actually doesn't go into the formula, it's just L and C. So it has some natural frequency. Because there's L and C, there's going to be current flowing back and forth, there's some oscillations. Now, if this frequency, natural frequency, it's determined by the inductance and the capacitance in the circuit, if this matches, if this is equal or very close to the frequency, angular frequency of the source, okay, then the current that this RLC circuit draws from the source becomes maximum. So you get the maximum current here. Okay, at resonance, when these frequencies are the same, the source frequency and the frequency of natural frequency of the circuit, when they're equal, then you get the resonance. That's the resonance point. At resonance, since the current is maximum, the power dissipated from the resistor will be maximum. So that also means you're gonna, if it's a light bulb, you're gonna get the highest brightness. Okay, so if you go back to the previous slides, you'll find that the impedance for our LC circuit was this one. Remember the negative sign here. Let me go back. That negative sign came from the fact that the VL and VC, they were in phasors in the opposite direction, so we had to subtract them. Okay, let me go forward. Okay, so that was the impedance Z, and if you want to find the current, you basically divide V by impedance. Okay, so now if you want to get the maximum current, what you would have to do is, so Vmax it's basically fixed. It's the voltage of the AC source. But if you have the minimum impedance, then you will get the maximum current, right? If the impedance is small, minimum, then you will get the maximum current. Now, when does that happen? Let's see from this equation. If these numbers are equal to each other, you will get 0 here, right? This whole term will be 0. Then the denominator will be small. Then you will get the maximum current. Okay, so when is this part 0? Well, if VL equals VC, okay, then it will give 0. So now VL is omega times L, VC is 1 over divided by omega C. Now if you solve for omega, okay, so just put this omega on the other side, it's going to be omega squared. Put the L in the denominator here, you will find that omega is 1 divided by LC. And this is actually the characteristic frequency of the circuit, right? So this equation, from this equation, we found what I actually said here. If the if this source frequency, angular frequency, is equal to square root 1 divided by LC, which is actually the characteristic frequency of the circuit, then we get the maximum current. Okay, now how do we use this in technology? We're going to come to that in the next slide. Again, this is the resonance condition. When the circuit frequency matches the frequency of the RLC circuit, you get resonance, and at that point, the circuit draws the maximum current from the AC source. Okay, let's go forward. Now let's talk about the applications. Now the first thing is that I'm going to talk about is metal detectors that you see almost everywhere, right? So metal detectors are RLC circuits that we just learned, where the large coils on the two sides so there are actually basically coils here, and there are coils here. So they play the role of inductor, L. So now there is an RLC circuit, so it has some particular frequency, natural frequency, right? You cannot really change it unless you change the values of L and C. But there is a way. If you go into the metal detector with some metal, okay, when a metal goes through the metal detector, it changes the inductance. Why? Because if you put some metal inside the inductor, it actually changes this value. So L becomes, let's say, L prime, some different number. If you change L, then if you change L here, then the frequency changes, right? Of course, the circuit always, it monitors the frequency. So it changes the natural frequency of the circuit. And this change is detected by the circuit in the metal detector. And the metal detector, of course, rings. It says, okay, the frequency should be 1 over LC, but now let's say there's some device here, it monitors the frequency in the circuit. And when you put some metal through the detector, it changes L, there are some coils here. It changes the value of it really doesn't change the coil itself, but because you put some metal inside the coils or between the coils, it changes effectively the L, which changes the circuit frequency. And this device here connected to the circuit, it says, hey, the circuit frequency changed to a different number, and then it rings. Okay, this is how metal detectors work. Okay, now as I said in the beginning, for radios, this is AC circuits and RLC circuits. Basically, they are the foundation of radios. Okay, so different radio channels, they have different frequencies, right? They broadcast at different frequencies. An RLC circuit with natural frequency F0, it will pick up the radio broadcasting at around frequency. So let's say the radio is broadcasting with F, frequency F, let's say 100 megahertz. If your circuit, or let's say your circuit frequency, the natural frequency of your circuit is 100 megahertz, that means your circuit, which is radio, actually this is a radio, it will pick up the radio waves, the radio channel of which frequency is the same, which is 100, let's say 100 megahertz. Okay, again, this is a resonance. So the radios broadcasting at frequencies other than F0, they will create very little current on the RLC circuit. So what happens is you actually get the radio waves. Let's say this part is the antenna. This part is the antenna. Okay, so the radio waves come to the antenna. So we are living right now in radio waves with all frequency, right? So all the channels, we are inside all the channels at different frequencies. They are all of them are coming to our radio, but our radio will pick up one particular frequency, right? Why is that? Well, it will actually pick up all the frequencies, but what is the frequency that will create the most current in the circuit? Well, it's going to be the frequency, that particular frequency, which would match the natural frequency of the circuit. Let's say if the circuit frequency is 100 hertz, so let's say 100 megahertz, FM 100 megahertz. If this is the natural frequency of my circuit, okay, now all the radio waves like 88 megahertz, 90 megahertz, 95 megahertz, all the frequencies are coming, but they will not create that much current in the circuit. Only the 100 megahertz, or the close number, only that frequency will create, well, actually it should be megahertz, will create huge current in my circuit. And that's why when you tune it to that radio frequency, even though the other frequencies are coming, because this is creating the most current in the circuit, you will listen to that that radio, that particular radio. If you look at this plot here, so the y-axis is the current, the x-axis is the frequency. Let's say your RLC circuit, the omega 0 or the F0 of your circuit is 100 hertz here. Let's say 100, something like 100 hertz. So the other frequencies that are coming to your antenna or your circuit, they also create some current. See, it's not 0. But the frequency that's exactly at this 100 or maybe 90 in this case, it creates the most current. And because the current is created by this frequency is maximum, you will listen to this radio station. Okay, now how can then let's say you want to listen to different radio frequency, let's say 150. Like, what do? Well, all you have to do is change your natural frequency in the circuit. So you have to change omega 0. How can you do it? Well, there are two options. You can change L, you can change C. So in the radios, especially the old radios, you have these devices that they're basically adjustable capacitors with moving in and out plates. So when you change the knob, when you tune the radio, you're basically changing the capacitance of the circuit. When you change the capacitance of the circuit, what changes is the omega 0. So maybe this curve, let me erase all of these. So when you change the capacitance, so F0 will change. It's not going to be 90 anymore. Maybe it's going to be 150. So it will be something like this, maybe. So now because the maximum current is now created by this frequency, 150, now you will listen to 150, the radio that broadcasts at 150 hertz. Okay, this is basically what tuning is. Tuning a radio for different frequencies, it means changing the capacitance in the RLC circuit. When C changes, the natural frequency, omega 0, of the circuit changes so that the radio respond to different frequencies. Again, whatever the frequency is, the natural frequency, again, the other frequency, it picks up a little bit also the other frequencies. The other frequencies, they also contribute to the current. But the frequency that's tuned that matches the circuit natural frequency, the characteristic frequency, it creates the most current, the highest current, and that's the radio channel you will be listening to. Okay, that's it for this lecture.